in algebra, we are given some equation and we're solving for the unknown. Say, here we just subtract 3 when we arrive at the constant. Sometimes algebra gives us nonlinear equations, which isn't going to be the topic here. We don't really care about these. We care about lines like x plus y is equal to 1, but this is rather easy, and we don't really care about just one line, but maybe two lines, like x minus y is equal to 3. This example is easy. For example, we would just add them together to get 2x is equal to 4, or x is equal to 2. This is the point of intersection. We would plug this back into either one of these. 2 plus y is equal to 1. To find what y is, 2 minus y is equal to 3. Isolate. Subtract 2 from both sides, y is equal to negative 1, or we can add y and then subtract 3, and we get the same, y is equal to negative 1, so we have 2 comma negative 1 as this point of intersection. Linear algebra would expand on this, and instead of just solving for 2, we can have a whole array of different equations. We would typically put them into a matrix and then solve, but basically we can have any number of variables that we can solve for. For example, if we wanted to say x plus y minus 2 is equal to 3, x plus 2y minus 3, I have this written wrong, x plus y plus z is equal to 3, x plus 2y minus 3z is equal to 7, 2x plus 3y plus z is equal to 10. How would you solve this? You could isolate and be like, okay, well, x is equal to 3 minus y minus z, and then we can plug that into each of these, and then find out what y and z are, and then we can get all these different values. Or another method would be to put this into a matrix. So what you would do is you would have each row, or each row would be a different equation, the coefficients for each. So we would have a column for y, a column for y, a column for x, a column for y, a column for z, and then a column for the constant, what it's equal to. So this would be 1, 1, 1, 3, and then 1, 2, negative 3, 7, 2, 3, 1, 10. You would solve this by the method of row reducing, which is not that bad, but it is a little tedious. So row reducing has 3 rules. 1, you replace a row with the sum of itself and multiple of another row. For example, we could do R3 is now R3 minus 2R1. This is not related to the example that I have right here. The second rule could be we interchange rows, meaning we change the order. Now R1 is going to be changed with R2. What this would mean would be that you just switch these orders. So instead of 1, 1, 1, 3, 1, 2, negative 3, 7, what it's going to be is now 1, 2, negative 3, 7, 1, 1, 1, 3. All it is. And then 3 multiplied by any non-zero constant. So that could be R3 is now 2R3. So that means this entire row would get multiplied by 2. Maybe I'll do this example, but maybe not. But when we row reduce, if it comes up with a solution like this, then that means there is exactly one solution. We could say x1, or x in this instance, would be equal to 3. x2, which we could say is y, would be 7. x3 would be z, equal to 17. In linear algebra, you really use x, y, z. You use x1, x2, x3, because there could be any number of variables, xn. Now, if we were to have a matrix such as then this is considered inconsistent, because then we have these zeros equal to 2, but that can never be a case because 0 never equals 2. So this would have no solution. If you get something like this, we can have x1 minus 7x3 is equal to negative 6. And then we also get x2 plus 3x3 is equal to 5. And then 0 is equal to 0 for the last line. We cannot solve more than this. This is consistent since there's no contradictions, i.e. 0 equal to 2. x3 in this case would be what's called a free variable. Since the ones right here are known as pivots. And a pivot is a first non-zero entry. Usually in row reducing, it's usually a 1. It has to be a 1. It marks the column where the variable is solved for. A free variable can take on any values, so x3 can equal, say, 2 or 3 or negative 100, etc. x1 and x2, because they are in pivot columns, they're going to be known as dependent variables. They cannot take any value, so their value is inherently tied to x3, so we can write it as x1 is equal to negative 6 plus 7x3. So if x3 is equal to 2, then x1 is negative 6 plus 7 times 2, or negative 6 plus 14, or 8. it's almost like x1 is a function of x3. Almost. I'm not exactly sure on that, but it just seems like it is. Going back to our original, this one, 1 1 1 3 1 2 negative 3 7 2 3 1 10. Row reducing this one would be, if we were to row reduce this one, it would be 1 0 0 negative 1 0 1 0 4 0 0 1 0. 1 cannot equal 0, so this matrix has no solution.